So a little bit about kind of formalized, we'll come back to that in more detail, but just to formalize a little bit supervised learning, there we have a training set of n examples, so that is pairs of inputs and the associated target value, and we call that a labeled training set. Of course, when we talk about unsupervised learning, we'll only have the x's, y is unknown, and what we do is that we train this conditional model, so we want to minimize the error that the network does on the training outputs. So we define a cost function and then we minimize that by a stochastic gradient descent method. And here I have illustrated a model that only has two parameters. We start at the point with a red arrow and then we take small steps opposite the gradient, so kind of these ellipses are like the contour lines in the cost function, so that's like a nice quadratic cost function in this case, and you can see that each dot corresponds to we're taking one iteration in the update, and eventually we'll end up in the minimum. But this is for when we are doing like not stochastic gradient descent. This is normal standard gradient descent. When we are doing stochastic gradient descent, it will look more like this. So stochastic gradient descent arises because we are usually it could arise different ways. For example, by adding noise to the gradient, but it could also arise if we compute the gradient on a subset of the training set. This is called mini-batch learning, and this has actually turned out to be the best method in practice. I'll come back to that later today. Yes, and of course an issue is overfitting. So this is exemplified here by Volkswagen's diesel engines, where they actually put some software in their cars so that they actually didn't exhaust a lot of NOx when they were in a test situation, but when they were left out in the wild on the roads, they would just to kind of maximize fuel efficiency, they will just pollute a lot, and so overfitting is when you fit well to the training situation, but when you see new examples, you are making not so good predictions. So a lot of the issues when you have these very big deep models is of course how to avoid overfitting. So we will spend a lot of time on talking about heuristics for avoiding overfitting. So here's a small example of how we can use neural networks. So this is the famous MNIST handwritten digit example. So we have handwritten digits from 0 to 9, and we want to classify whether it's 0, 1, and so on up to 9. We get as an input, we get these small 28 by 28 images. And we have 60,000 of those, so we have 6,000 for each type of digit, and we will then train a deep learning model to do this. And the model that I will walk you through in the next slides achieves an error of 1.2%, which is pretty good for this kind of task. So here's the example model. So we just start out, as I said, by kind of unfolding the image. So we have a long vector, which is this 784 input dimensions, each corresponding to 1 pixel, 28 by 28. We feed that into the network, and then we have to just decided that we want to have 225 hidden units in the first layer and 144 in the second layer, and in the end our output is the 10 classes, so we have a 10-dimensional output. So so we have this network. So in the first two, as I said, in the first two hidden layers we use the rectified linear as our output function, and then in the last one, because we want to have this classification system, we use the softmax, and the softmax has this nice property that we can interpret the outputs as probabilities, and that is achieved by having this definition of the function as defined there. I'll come back to that. So you can see now that we have in the first layer weights, I use superscript 1 to indicate that. Then we have this 225 times the number of input dimensions and so on for the next layer and the third layer. And then also in this slide I use a little bit different notation, so I actually explicitly write the intercept with this b term. So we have like a 225 dimensional offset intercept term in the first layer and so on in the next layers. So a little bit more about this softmax. So here's the definition of the softmax, and it has two nice properties. One is that because of this exponential function I have here, that it means that the output for each dimension is always non-negative. And because of the denominator, then the output will sum to 1. So that means I can actually interpret the output from each of the output units as a probability, and I'll interpret this as a conditional probability for that class. So this is a very nice way to construct a network which is a probabilistic classifier, right? So that means that, for example, I can take the 5th output unit from my network here and interpret that as the probability that my label is 5. That means if I put 0 at the 10th class. Yeah. A little bit about activation functions. So why don't we use just a linear activation function? This is this kind of back of the envelope calculation down here showing why we should not do that. So here we have replaced the two ReLUs with linear models, so we can just put that into the expression, and you can see now that in the end we have a model that says that h2 is just a linear function of x. So that means that the feature transformation we make here can only be linear if we use linear activation functions, and this is why we need to use the nonlinear activation functions. Otherwise we could just have collapsed the network to a shallow network. Yes, okay, so here's how the weights, here we've actually depicted all the weights in the first layer. So remember that the second dimension of the weight matrix in the first layer has the dimension of the inputs, right? And this is this is all the pixels, so we can reorganize them again as the original image, and each of these 225 squares represents then the weights for this specific unit. And this is after training, and you can see what the network has kind of picked up here is it picked up kind of features that corresponds to generic 2s, or maybe parts of 2s and 3s and all the digits, and in that way it can actually kind of extract features that will be subparts, and then in the subsequent layers combine these to form a large activation if it sees the right kind of digit. So this is also illustrated here where we follow the signal flow for 16 different examples. So we have taken the first 10 as just kind of 10 examples from the test set, and from 0 to 9, and then the last 6 are also from the test set, but here we have added some noise. And now you can see in the next plot, you can see the activation in the first hidden layer. You can see it becomes kind of sparse, and this is because of the rectified linear. Remember that the output of the rectified linear is 0 if the argument is negative, and then it's linear beyond. So we only see all those that has a positive input to that hidden unit. And roughly when you wish, then in the end you can see the class probabilities that are kind of laid out from 0 to 9, and you can see that in this, for these 16 examples, the model actually predicts the right class. So this means that actually the activation of these inputs close to the output should of course be kind of similar if we insert the same input. So that means that roughly if we get a 1, for example, we have 3 1s in this example, the second one and like 2 in the last row, you can see that kind of the activation in the second hidden layer looks somewhat similar. So at that point in the processing of the input, it has kind of find out that we have a 1, and it should activate the patterns that will correspond to predicting a 1. And we'll come back to that when we kind of look at a video that shows us how we can dive into the prediction made by this image classification network called AlexNet. Yes, okay, here's a little bit on the sparsity. So here in this we have kind of shown the output of the first hidden layer and the second hidden layer for a specific example, and you can see what was not shown is kind of all the outputs that are 0, but you can see there's like some of the inputs, some of the outputs are actually non-zero, and this is kind of what we live from. But this is far, as we also could see in the previous plot, this is far from all of them that are actually activated here.